Hi, everyone. Welcome back to the Physionic podcast if you're coming back, and welcome to the Physionic podcast if you're brand new to the podcast. My name is Nicholas Verhoeven. I'm a PhD student in molecular medicine, and I have my master's degree in exercise physiology. And that particular degree is going to be of special importance this episode because today I'm going to be discussing something that I thought I'd figured out, but apparently that is not the case based off of a new paper that I've just run across. So what am I talking about? Well, in the past, relatively recently, maybe a few weeks ago, 3-4 weeks ago, I released some content on how phospholipase D was a major player in the translation of muscle stretch or the stimulus of a musculature, and that translation from the mechanical aspect, the actual movement of that musculature and the force production of that musculature, into a signal that would then lead to increases in muscle growth so that the muscle would end up growing. Now you need some sort of way to translate that. You can't just have a muscle stretch and contract, or will go through its contraction phases, if that's eccentric or concentric, and then what? What happens after that? So I read a paper that was trying to make the association between a particular enzyme by the name of phospholipase D, and there are a number of different phospholipases, but specifically for PLD, and how that was translating that signal from the musculature to allow it to grow. Now, that paper seemed like it was creating a pretty strong association between PLD and the increases in muscle size based off of muscle stimulus, so the actual musculature generating force. And well, it turns out that may be completely wrong, or at least it may not be nearly as much of a factor as this other system that I'll be discussing in this podcast. And so I'll be elucidating that a little bit in this podcast, but I will have specific content that's going to come out in video format if you're interested in that. And that'll come out probably most likely next week, if not the week after. So certainly keep your eyes peeled for that. So let me kind of describe to you what's really been going on. Like I said, it's a translation of the muscle cell or the muscle belly in general. So if you look at your arm, right, and you're contracting, let's say you flex your arm, and let's say you've got a dumbbell in your hand and you're lifting a certain amount of weight where your muscle gets tired, that's a stimulus. So you're consciously deciding, okay, I'm going to create the stimulus, and therefore then I'll be able to produce force, and therefore I'll be able to grow my musculature. Now, but what actually translates that down to the cellular level, to the molecular level, actually? And like I said, in I think 2006, there was a paper that was first to elucidate one of those mechanisms, which was the mechanism of phospholipase D. And I have content on that. And I'm actually incredibly thankful that I decided to stick to my guns, because I read the paper, and there were like one or two inconsistencies that I thought were relatively suspicious, but I didn't think anything of them, but I did make notes of them, and I made sure that I worded that piece of content around phospholipase D based on that paper in a way that left the door open for other possibilities. And I'm really glad that I did, because this other paper that I'll be talking to you about definitely puts a stamp of approval on exactly that. So it's really a chase. It's really a mystery, trying to figure out what really translates the mechanical force of the mechanotransduction into a molecular signal to tell the cell, okay, now grow. So, like I said, in 2006, I think there's this paper that was making the association between PLD and the growth of the muscle cell, or the musculature in general. So a previous study, what they did, and they had two different ways of showing this, which you'd think that with two different ways, that would be pretty good evidence, but apparently it's not going to be, as I'll explain in a little bit. But this study looked at PLD in cells in muscle cells, and they inhibited it with a drug known as neomycin. And so that was the first line of evidence, because then they saw decreases in a downstream protein of PLD. So what PLD does is it converts a molecule known as phosphatidylcholine into phosphatidic acid. Now, phosphatidic acid then will bind mTOR, which is mammalian target of rapamycin or mechanistic target of rapamycin. There's a number of different names for it, but essentially it's the master regulator of protein synthesis and cell growth. And that's really all you need to know. So phosphatidic acid that's produced by PLD will then bind mTOR and then activate it to then phosphorylate or activate another protein named P70. So you've got PLD activity increases, you've got phosphatidic acid concentrations increase, mTOR increases, phosphorylated P70 increases, therefore you have cell growth, or that's the assumption that then you have cell growth. So you have muscle size increases. So hopefully that string, it's essentially everything increases. If everything's increasing, then everything's increasing in terms of the muscle size. So that's a good sign. However, with neomycin, what they did is neomycin inhibits PLD, so it stops phospholipase D. Now, here is the thing. That experiment has a twist to it, because inhibiting PLD by neomycin is, you have to look at how it does it. So how does it inhibit PLD? And it turns out that it inhibits PLD by binding or inhibiting another molecule known as PIP2, PIP2. Now, PIP2 needs to bind PLD to allow PLD to actually function. So neomycin will inhibit PIP2, and therefore PLD can't function. So they saw decreases with the phosphorylation of P70, that downstream molecule of mTOR, and therefore they thought, okay, well, this is a pretty good sign. Then they did another experiment. They did essentially the same thing. They wanted to confirm this, so they used another inhibitor known as 1-butanol. Now, 1-butanol is you could call it like a competitive reactant to PLD. So while PLD takes phosphatidylcholine, that molecule, and turns it into phosphatidic acid, it also has the ability to turn a phosphoethanol. It allows for the use of an ethanol to create a phosphoethanol. So the use of 1-butanol, which is one of those ethanols that can be used by phospholipase D, allows, if you have an oversaturation of this 1-butanol, then the PLD will be busy using that as its substrate. It's going to use that as its reactant, as opposed to using phosphatidylcholine, because phosphatidylcholine concentrations will be at a certain level, and if you just keep pumping in 1-butanol, eventually you're just going to have an excess amount, and therefore PLD will just start using that and create another substrate instead of phosphatidic acid. So they did that, and yet again, so through a different version of inhibition of PLD, or more like kind of distracting PLD by going a different direction instead of creating its usual product of phosphatidic acid, they did see a decrease in phosphorylation of P70. So great. So that's more evidence then that this has an effect on phosphorylation of P70, and therefore it's going to decrease muscle cell size, presumably. And then they did a control for that by adding 2-butanol, which does not interact with PLD. So they added 2-butanol, which is very similar in terms of structure to 1-butanol, but it doesn't have the effect on PLD. So that's a control that they ended up using. So it gives some evidence. Then you're like, okay, well, now we've got two different methods and we've got controls that that show that if you decrease PLD production of phosphatidic acid, then you see decreases in phosphorylation of P70, and therefore you'd see decreases in muscle size. So that's all great. Here's the thing, though. According to this new paper that I just read, where they were referencing this previous paper, they ended up having a lot of doubts based off of the results that were taken from this 2006 paper on PLD. And the reason is because of a number of reasons. Let me touch on 1-butanol. 1-butanol seems to have a lot of off-target effects, meaning that it not only affects PLD, but it actually affects other areas of the cell, other reactions within the cell, and therefore you can't necessarily attribute that the effect that you're seeing is specifically because you're inhibiting PLD. You could be inhibiting other things, and therefore that's why you're seeing this decrease in phosphorylation of P70 and presumably this decrease in phosphatidic acid production. So that caused some hubbub there. And that's really what they focused on. But I also found some issues with the neomycin treatment, so the first inhibition that I was talking about. So in this second paper that I will be presenting on in more, with graphics and all that on the video content, they did a lot of the same experiments, but they wanted to use different inhibitors that were a little more specific, and they also wanted to investigate some other areas. So they wanted to figure out, okay, well, let's check if PLD truly is going to have an impact, because what the previous paper showed is that PLD activity actually remained largely the same with stretch, which I actually took notes on this, and I remember I wrote down that was pretty suspicious, that the activity would stay the same, but phosphatidic acid levels did increase. So it was a little bit of like waffling back and forth. It wasn't very conclusive evidence that phosphatidic acid was rising because of an increase in PLD activity, because we didn't see an increase in PLD activity. Maybe an initial rise, but then later on it just turned out that it wasn't. It stayed at basal levels. So phosphatidic acid was continuing to rise, however. So there's a disconnect there. So that creates some suspicion. And that's why I'm really glad that I ended up mentioning that there's only an association. And even in my notes, I said that it was strange that there was no increase in PLD activity with the rise in phosphatidic acid. So anyway, this new paper ended up inducing stretch on muscles, and they saw and they confirmed that you see an increase in phosphorylation of P70, so that downstream molecule of mTOR, through mTOR specifically. And then they wanted to assess PLD, so they assessed PLD activity again, and they found that the same thing, that there was no increase in PLD activity with stretch, which is actually essentially the same that the 2006 paper found as well, or the earlier paper found as well. But phosphatidic acid levels did rise. And here's the thing, though, then they decided, well, let's use a different PLD inhibitor known as FIPI, so FIPI, that's what we're going to call it. FIPI specifically inhibits PLD. So they used this PLD inhibitor, and then they still saw phosphorylation of P70, which is not a good sign for PLD as the mechanism for that transduction of stretch or stimulation of the musculature into a chemical signal through phosphatidic acid, or really through any mechanism. So it essentially implies that PLD is at least not the main contributor to this translation of mechanical signal or mechanical action to chemical signal. So because they're inhibiting PLD, but they're still seeing this effect on the phosphorylation of P70 with the induction of stretch on the musculature. So that made things really suspicious. And not to say that the first paper they hid anything or anything like that. They just messed up potentially on the different inhibitors that they use. They should have used more specific ones as opposed to using such general ones that had so many off-target effects. And I'll explain the issue with the first inhibitor, neomycin, in just a second. So what this second paper also did was they found that with stretch, there were increases in diacylglycerol, which is another molecule. I didn't explain that one yet, but diacylglycerol levels increase, and diacylglycerol is actually the reactant, or the beginning molecule, which then interacts with an enzyme called diacylglycerol, makes sense, kinase. So it phosphorylates diacylglycerol and creates phosphatidic acid. So here you've got another source of phosphatidic acid. So then they're thinking, okay, well, if diacylglycerol levels increase with the stretch of the musculature, the stimulation of the musculature, then that could imply that this mechanism of increased phosphatidic acid is actually not due to phospholipase D, but could actually be due to diacylglycerol kinase. And then they decided to test, okay, well, then let's test diacylglycerol kinase activity and see what happens. And sure enough, although the overall levels throughout the cell, the overall levels of diacylglycerol kinase activity did not increase, which is certainly suspicious, when they specifically looked at the diacylglycerol kinase activity, or DGK activity, on the membrane of the cell, which is probably the most prime location to put an enzyme if you're trying to sense the stretch of, well, the membrane, right? You're trying to sense the stretch of the musculature. That would be a perfect spot to put an enzyme, evolutionarily speaking, biologically speaking. And that's what they end up finding. They end up finding that the DGK activity in the membrane specifically was actually massively upregulated as a result of the stretch of the musculature. So now they're starting to piece things together. They're seeing diacylglycerol levels increase. They're seeing phosphatidic acid levels increase. And they are confirming that DGK activity, the actual enzyme itself that converts diacylglycerol to phosphatidic acid activity, does increase, unlike PLD. So then they wanted to know, what happens if you knock out DGK? If you create a mouse that does not have the genes that encode for DGK, therefore they can't make their own DGK, diacylglycerol kinase. So with a diacylglycerol kinase knockout, they did see that there were reduced levels of phosphatidic acid production, but that phosphorylation of P70 was still elevated. So there's an interesting thought as well. So phosphorylation of P70 is reduced when DGK is knocked out with muscle stretch. So DGK is likely going to be an mTOR dependent system in that case. So now they're trying to create this story in this different direction, away from PLD and more towards DGK, because now you've got these two different systems that produce the same molecule, phosphatidic acid. And presumably phosphatidic acid still binds mTOR, and that's where you're getting that phosphorylation of the P70. So this is starting to spin the table away from PLD. Not to say that necessarily that PLD has no impact, because it does produce phosphatidic acid. So it likely does contribute to that pool of phosphatidic acid, and therefore it contributes to the increases in muscle hypertrophy, or that translation. But maybe the primary mechanism by which that actually occurs is through DGK, through diacylglycerol kinase. But the thing is that it's also possible that, so PIP2, which I mentioned is what neomycin binds and inhibits, and that's what that first paper is using, one of the inhibitors they're using to inhibit PLD, PIP2 can actually be converted to IP3, which is another molecule. You don't have to worry about that. But the second molecule it gets converted to, so it gets cleaved into DAG, or diacylglycerol, which is the molecule that diacylglycerol kinase uses. So here, in this situation, then that means that neomycin may have been inhibiting PLD, sure, by inhibiting PIP2, but in that first paper, what they didn't control for is it was potentially also inhibiting, and most likely this was the case, that it was also, without them thinking about it, without them realizing it, they were also inhibiting DAG kinase by reducing the levels of PIP2. If you have less PIP2 substrate, then that means you're going to have less DAG substrate. If you have less DAG substrate, what does that mean? Well, then diacylglycerol kinase will have less DAG substrate to convert into phosphatidic acid. So you're knocking out both mechanisms, PLD and DAG kinase, as opposed to just knocking out PLD, which is what they thought that they were doing. So it puts some big holes into that first paper, and it gives more credence to DAG kinase. However, I don't think that's the end of the story, because I think what could also be the case, because we have recognized that PLD, or phospholipases in general, because they're a whole family, there's like phospholipase C, phospholipase D, there's a few different ones, a few different iterations, a few different variations. Now, those are embedded into the cell membrane, and there has been evidence. I know there's a Nature paper that looked at how when the muscle cell contracts or it shortens, that the PLD will actually move to its substrate of phosphatidylcholine. So it'll be physically moved across the membrane so that it can interact with its substrate to create phosphatidic acid. So, while there's a good amount of evidence now against PLD being the main mechanism, that doesn't necessarily mean that another phospholipase couldn't also be contributing. And one that I'd like to just quick mention, although I haven't researched this in great depth, but PLC, so phospholipase C instead of phospholipase D, is also in the membrane, and here's the kicker, it generates DAG. So it generates diacylglycerol. Therefore, that could be a contributing factor as well. So that could be a reason why you're seeing increases in this diacylglycerol level when the muscle cell or the musculature is being stretched. And that's going to increase the substrate that's around for the diacylglycerol kinase to then convert that to phosphatidic acid. So you've got these three enzymes that are just like playing, like we're chopping it up. We're trying to figure out what this mystery is, like which one is truly the big player. I will say, I think that the evidence right now seems to be pointing in a more concrete fashion towards diacylglycerol kinase. However, it is still possible. I do think, I think pretty much unequivocally that PLD does play a factor, because it does create phosphatidic acid, and phosphatidic acid is the molecule that binds mTOR, which is then going to lead to this increase in muscle cell size. So some really, really intriguing stuff here, and I'm excited to release this new paper, for everybody to kind of consume, to be able to look at the graphs and stuff like that. And it's nice that it's contradictory to something else that I've posted before, because it creates a little bit of debate, it creates a little bit of discussion, and it shows that a paper can still be well done at the time, or I mean, it had its flaws. I'll put it that way. They had good intentions, and they thought they were probing what they thought they were, and they technically were, but they were also confounding their own results by using the particular inhibitors that they were, neomycin and 1-butanol. So using more specific inhibitors might have helped them a lot in terms of getting to the correct conclusion. So based on the current evidence, diacylglycerol kinase is probably the primary contributor to this conversion of mechanical signal into chemical signal, and phospholipase D may contribute, but it's not going to be a major player. It's not going to be the major player. And I would postulate that potentially PLC, phospholipase C, may also have an impact. And I think I don't have this written down, but I believe, and don't quote me on this, but I believe that there's another protein that PIP2 actually binds. I believe that protein is protein kinase C, PKC, not PLC, PKC, and PKC will actually bind to or increase the activity of mTOR. So it's possible that you're seeing another mechanism there as well, but I'm not going to investigate that for the time being. But that's where we stand right now. And I'll be really interested. Of course, I'm going to leave the previous video up, the previous content up, but I'll add amendments so that people are aware that, you know, some of that data has been updated now, and some of that information has been updated, and they should check out this new paper that's come out to kind of make sure that we're on the right track. So hopefully you found this informative. I know this is really molecular based. I hope that you're able to follow. If you weren't, I mean, certainly check out the video. I think the video of that's going to release later on. I do think that ultimately I'll be able to put up like graphics and stuff like that, so you'll actually be able to visualize some of this stuff. And I'll try and keep things relatively simple in terms of how I'm explaining things as I try and do, except for obviously in the podcast, I'm kind of going off the cuff. The second thing, the one last thing I want to say is probably next week, I'm going to have a friend of mine who's going to be talking about fungi pathogenesis. So talking about how fungi can be detrimental to our health, and talking about pathogens in general. So understanding how microbes affect us and things like that. So I'm really pumped for it. It's not something that I know a whole lot about, especially with fungi. So it's something I want to delve into deeper. You know, of course I want to delve into everything deeper, so that's not a huge shock, but it'll be a nice introduction, because this will be the first time ever that I've talked about real fungi, or I've had anybody talk about fungi on Physionic. So hopefully you have that to look forward to. Hopefully you're as excited as I am. She's really, really smart. She knows quite a lot about this stuff as an immunologist. So it'll be cool to have her on the podcast. Okay, well, with that said, I wish you a wonderful day, and I hope I have the absolute pleasure of speaking with you in the next one. Have a good one. See ya.